economics.
Did you like economics?
I did. I almost got a minor. I'm one class short of a minor in economics. I loved economics. And I probably would have loved physics too. I just probably had a bad experience.
Yeah. You talk.
Huh? Oh, I like PDEs. It's ironic. Yeah, I would have probably liked physics just fine. So, yeah, but you know what I really like when Mark talks is the experiments. To be able to see some of the things that you're talking about using calculus in the lab. That's what we're missing. It'd be nice to cross-teach that.
Yeah, but
Or somehow merge the calculus or whatever the calculus you're learning, you're also implementing it in the university of physics. Dean Hamden and I did that one semester. It worked really well. So my students in the calc class teamed up with, they were taking him for physics. And then him and I could piggyback off and say, I'm going to teach this week, so why don't you teach the math to go with that? And then they could really see that connection. It was fun. All right, so I hope this was helpful to make a slide which has the homework. And so the homework today, what I'm going to do is I'm going to give you a take-home quiz for this week where you can still work in groups, and I've got them all marked. And I'm still available to you, very available to you, because I'm in Minnesota and I don't think there's much to do there, right? So, and it's very cold. I probably won't want to go outside. And then the homework that's, I'm going to assign some homework that's not for grade, which is more computational, just to get your feet wet. Today, we're going into the last stretch of the abstract algebra course, actually. And it sounds like, well, we just did groups. How could this possibly be the last stretch? Well, there's a point to all of abstract algebra, and I told you that it's about solving equations. And groups are the algebraic structure. That's actually going to be my little theme in the background, Kristen, so you don't have to actually see it. But groups formulate the structure of all of these other types of abstract algebra entities, like fields and integral domains. Turns out that rings are the weakest of the next form that you have. And the hardest part is distinguishing between all of these different definitions. So this week, again, I said I'll give you a take-home group quiz, and it's directed towards getting you ready for the exam, so it's not something that's independent. Some homework we assigned that I'm going to compute factor groups, but not to turn in. I just want you to get used to doing that. So for example, just these are out of Fraley. You can find them in there. Just compute some of these. Know that you can follow the definition and compute some of these. I think some of you are doing it anyways. But if you haven't actually computed a factor group and can see what it looks like, get your hands dirty. Do it. And actually do some computations in these factor groups. You know, find the order of one of these. Just take an element out of there, find the order of that element, and see what that looks like. We did a little bit in class, but I'm worried that it's such an unfamiliar definition, even though it is an abstraction of modding integers mod n. It's like David was saying, it's kind of such a general, weird definition that when you have to work with it, you start to lose touch with reality, that's the definition of mathematician. Totally out of touch with reality, right?
Yes, I am.
You're a mathematician. You just defined yourself. Okay, so here's one that I'd like you to actually look at. The definitions, the difference between homomorphisms and isomorphisms, which in my abstract algebra world we shortened down to homomorphs and isomorphs. So if I have a group homomorphism, and let's suppose I knew that was even stronger, an isomorphism, I know that the order of whatever element I have in the range is the same as the order in the domain. Isomorphism is the full thing. You have an entire code book from one group to the other. But if phi is not an isomorphism, a true homomorph, is this still going to be true? So if it's true, prove it. If it's false, find a counterexample. And you should be able to get this within 2 minutes, because almost anything that's a true homomorph will give you a false. The second problem I'd like you to look at is if you have a homomorph that goes between two groups, is it true that the group 1's order is going to be the same as group 2's order? You already know that can't be true. I just want you to actually see it with your hands. because I showed you that diagram last time, right, with the big group going down to the small group. So it's not possible. If you have a true homomorph, it's not going to be true. If it's false, can you find a condition that you could add in between isomorphisms? Isomorphism is going to be true, right? That both groups will have the same order. In fact, you don't even need the isomorphism. You just need a bijection between the two. You don't need the group property. But is there something in between homomorph and isomorph that you can add as a condition and get G1's order to be the same as G2? Play. So just to clarify, what I'm asking is, can you fill in a blank there? That's not isomorphism. If phi is a homomorphism between G1 and G2, and something else, then the order of G1 equals the order of G2. Just asking. Prove it. Okay, so we're now in the last stretch. This is 18 to 21, a little bit. Right at the end, we're going to be doing extension fields and solving polynomials in extension fields, all kinds of fun things like that. But I would say that the bulk of what I'm taking today is rolled into 18 to 21. They're all connected to each other. They're not separate sections. So some of you took Hungerford. How many of you used Hungerford for your undergrad class? So that book starts out with rings. Ted Williamson and I just talked how much we like starting out with groups, because really what you're going for is group under both operations. That's where you like to end up. So if you know groups really well, that's where you're trying to head to. If you have a ring, what you have at minimum are two binary operations. You have plus and you have times. The times is new. It's a set. The first operation is usually called addition. The second operation is multiplication. And number one, under addition, you have an abelian group. So that's why groups are important. Multiplication, you only have one of the group properties, and that's associativity. And finally, you have what's called the distributive law, the left and right distributive law. That means A times the quantity B plus C is A times B plus A times C. And also you have it on the on the right, which I'm not going to switch the slide yet because people are taking notes, but on the right you have B plus C with A on the right also distributes in. There it is, right at the top. So what part of this set? It's everything. Rings is the weakest of all the grand finale sections. The strongest is fields. That's the little bullseye in the center. A commutative ring. Oh, I meant to bring this book to you guys. It's a wonderful book about linear algebra on commutative rings. So you did linear algebra on fields. That would be a nice, fun class. I'm trying to think of a 495 class that would not, they wouldn't sign up for it though. So there's commutative rings on the grand scope of the Venn diagram. It's inside, it overlaps some of the other pieces. What the commutative ring is missing, it's missing a multiplicative identity. So commutative rings have addition, abelian group under addition, you have associativity, you have abelianness under multiplication, but you don't have the identity. A ring with a multiplicative identity has an element 1 that behaves like an identity. It leaves things unchanged. That's that side. Commutative rings and rings with identities have an intersection, so they overlap each other. So, but there's stuff that doesn't overlap. Can I find something here? A true commutative ring that doesn't overlap the part with the identity. So I didn't give you any standard examples. You have so many examples now at your fingertips, right? You could have Z2 with addition and multiplication. It'll work. It's a ring. So sit down as a group and see if you can find an example of something that's truly here, that's a commutative ring, but doesn't have a multiplicative identity. That's not trivial. Have you been talking to him? Yeah, in class, work together.